I'm a C++ embedded developer, and that's should be a kind of a hint as to what I'm going to talk about today. The only other talk I've ever done is a quick lightning talk, which featured my hardware synthesizer, which it crashed constantly during the presentation and was a complete nightmare. But luckily, it was actually supposed to crash because it used the crash to generate a tone, and then I modulated the frequency of the tone by modulating the frequency of the crash. So it kind of worked out pretty well. I called it Crash Synth. I spent half of my career working on these things, digital mixing console, and the latter half I still work for Roly, and we make fun little musical instruments. Alternate title for this is just to talk about doing embedded programming in C++. A quick note about undefined behavior, in case it's not like drilled into your head, which it probably is because Tim O'Ryan and various other people talk about it all the time. But the way that I put it is that C++ is pretty complicated, and you can do all sorts of things with it, including misuse the features that are given to you. And generally, the only thing that they define is the stuff that they've thought that you might use it for, right? So if you're abusing it and doing something weird with it, then that's undefined. There's a great talk by Barbara and Ansel all about this stuff, which I recommend. So I'm going to show you some code, and hopefully you're going to jump out of your skins and chuck me out of the room and go a little bit crazy, but try not to. It's not pretty, but and you shouldn't really be comfortable running this code, and just like you shouldn't be comfortable reading it. Really, you should take one look at this and just walk away. But bear with me for a sec, and I'll try and break it down so you can understand what this actually does. This is an entire program, and firstly, we write some magic numbers into the address of some other magic numbers. Great. Then we wait for those memory operations to complete, brilliant, with a little inline assembly. And then we write some more magic numbers into some pretty abstract memory locations. And then we're going to wait for those to complete, do one more operation, and go to sleep. That's all this does. It just writes a bunch of memory and then goes to sleep. Can anybody think of what this might do? Any ideas at all? Yeah?
I'm going to guess that it's putting maybe something like Hello World and doing a syscall.
It's kind of like Hello World, yeah, sure.
No.
Any idea? Sorry, the suggestion was that it might be like Hello World. So, yeah, kind of.
And the last one might be doing a syscall.
Sure. But what do you think might happen if I ran this on Phil's laptop here? Yeah?
The memory addresses might be completely different or wrong, and I have no idea what OX4 and then some numbers is.
Yeah, perfect. It's going to segfault. It's going to just say, that memory address is absolute nonsense. What the hell are you trying to do? I don't know what you're doing. I'm going to crash. It's just going to crash. It's not going to work. However, if I were to run this on my little dev kit, which features a particular... Is that playing? It's supposed to be a video. Okay, there's no video. That's, oh well, that's what happens. So, I guess because it's undefined behavior, we lost the video. But what is supposed to happen here is you're supposed to see my dev kit, and it's supposed to just be blinking at 1 Hertz. It's just, this program is actually Blinky. So Blinky is the embedded equivalent of Hello World. Because maybe you don't have a screen, so you can't print Hello World anywhere. So what do? Maybe you've got an LED, so you're going to flash your LED. So now that I've told you what it does, now you can all read this and understand it, right? You all know what it does. So job done, right? Do I have more time? I guess I got more time. We'll dig into it. In order to figure out what this does, we need to read the documentation. Oh, what joy. I knew you were going to be excited about this bit. So I thought I'd spend ages on it and made loads of notes. way too many notes, so it's incredibly annoying. So let me introduce you to the manufacturer's documentation. The manufacturer in question that made the chip that was on the dev kit that you didn't see successfully flashing, which you're just going to have to trust me, they kindly split up all their documentation into a whole bunch of different data sheets. One of them was like a technical manual for the real nutcases, and then another one's a technical manual for people who want to know what they made a mistake when they made the chip. And this one is the reference manual, which is great. This is the one we want. The reference manual is going to tell us what we've just written. And it's really, really, really hard to describe what is actually happening here. Because what we're doing, if we look at the number that we're writing to this particular memory address, we'll ignore what the memory address is for the time being, but we're writing this number in. If we look at it in binary, we see that we're setting bits 2, 4, and 17 high. Everybody see that? And what that's going to do, if we cross-reference the documentation, it tells us that by default, we're going to be setting, the default settings are to have bits 2 and 4 high anyway. So the one we're interested in is bit 17. Bit 17, when set to a 1, I don't know if you can see it here, but bit 17 is attached to something called IOPA. IOPA is kind of access to the port pins on the device. And if we look at the documentation for the schematic of the board that you didn't see, then we'll see that port A happens to be connected to the LED on the board. So this is not a coincidence. So if we do the same thing for the rest of the code, we can kind of fill in what these lines actually do. These two switch on peripherals. I'll go into peripherals in a moment. And these set up the timer A pin, attach it to a timer. And then if you're still following me, these set up a timer to tick at 1 Hertz and output it to the pin. So that is how we get our blinky. And it's a real shame you didn't see it. I'll just do this. It's kind of doing this, on, off, constantly. And the unique thing is that the CPU can go to sleep while this is happening. Because once we've set up the hardware to do this job, there's nothing else to do in our program. It's just a blinky program, and if we're just doing it all in hardware. So it's incredibly efficient, I think you'll agree, because the CPU is doing nothing. It's free to do other things. In this case, absolutely nothing, just go to sleep. So that's kind of what I'm trying to convey is the usefulness of this, the power of a microcontroller, because the microcontroller itself is very slow, doesn't have much memory, can't do an awful lot of things, but it's got peripherals. And I'm going to have a little sip of beer and a deep breath, because peripherals are an absolute nightmare, and I have absolutely no idea how to explain peripherals to you. It's, I've already said half of my notes, and I'm going to read some more, and I might wrote way too many notes. There's peripherals are they're kind of like sub-processors. Imagine you've got your CPU, but then you've got loads of little extra processors, and they're only good at doing specific things. Maybe you've got one that does USB. It does USB really, really, really well, but it doesn't do anything else. You've got another one that's the timer that we're using to tick. It does that, it doesn't do anything else. It's configured by oh yeah, this is the manufacturer's documentation for the peripherals. I hope you can all read that really well. Yeah, don't worry about it. This is an example of how you configure those peripherals. You just write these bits in these weird memory locations, and magic sort of happens. Or it doesn't, because if you get it wrong, it won't. And you will get it wrong. This is an example of the behavior of some of these memory mappings. These are kind of weird types. This kind of shows you, I hope, the problem with this whole thing and using high-level languages like C and C++ to do this stuff. Because we're pretending that this is memory, but it's not really memory because, all right, some of this memory I can read and write to it, but some of it is read-only and some of it's write-only, which means if it's write-only and I try to read it, what happens then? Well, it's completely undefined what happens. You could crash, probably you'll crash. Excuse me. Sometimes the read clear is pretty good, you read it and then it gets reset to 0. Or read clear, read clear 1, you can either read the bit, it's really complicated, you can either read the bit or you can set it to 1, which will clear it to 0. And read clear write 0 is, you can read the bit and if you write 0, it sets it to 0, but you can't write 1 to it because that would make it go crazy. You can clear it by reading it, okay, great. Or you can reset. Writing 0 has no effect. Okay, fine. Reserves are my favorite because you don't have to worry about reserve too much. Just don't do anything with it, don't touch it, don't even look at it, it's not even there. What's next? Yeah, so any idea why this might be a bit of a problem? Well, okay, yeah, I'm doing the talk. All right, so the problem is, if I just let the compiler let me write all these memory addresses, it can do all sorts of funny things, right? Like rearrange those memory writes. So what I have to do here, the reason that I've got these assembly instructions in these weird locations is that I'm blocking here. DSB basically is a barrier to any memory instructions. So once it sets those two, it can do those two at the top in any order, but then it has to barrier, it has to break at this point because everything below it depends on those settings being set correctly. If some of these settings are right into the timer, if I haven't switched on the timer, then nothing's going to happen. And so I break again at the end before I enable stuff, because if I enable it before it's been properly configured, it's also not going to work. And what's next? Here's another example. The manufacturers will give you all sorts of crazy code like this. The bit that we're interested in here is this while loop. So I've rewritten it in modern C++ for you. It's way more readable, right? And basically what we're doing is we're looping and we're reading that memory location on every iteration and we're waiting for it to set to 0. This is kind of during setup, you're setting something and then you're going to wait for the hardware to tell you that it's ready to continue. So we have to wait for that to go to 0. But the problem is that the optimizer is going to come along and it's not going to understand what we're doing. It's going to see us reading the same memory address and think, well, I've got a really good optimization for this. I've got a fantastic idea to make your program so much quicker. And it's absolutely right. It's made our program so much quicker and smaller as well because it's removed that code. And maybe it's put this in its place, but we're not actually going to read the result. We're not really that bothered about this. So it's going to just remove the whole thing. And why not? So I'm wondering if anybody knows what the way around this is, because you've probably seen it.
Volatile.
Yeah, volatile. If we shove volatile into that reinterpret cast type, then all these problems disappear. And that's because there's this kind of loosely written, loosely defined, or maybe it's well-defined, Tim can tell you whether it's well-defined, kind of agreement between the embedded developer and the compiler writers that if I shove volatile anywhere, then it means the optimizer can't touch it. Don't assume anything about this memory location because it can change from under your feet, because the hardware can change it. So don't touch it. Right, what's next? Before I hit the button, because it could be a big surprise. It could be a video that doesn't work.
I have a mouthful of almonds, I'm very sorry. In the macro that was there in the original one, is there volatile there? When you originally showed here's how I've rewritten it, had you purposely removed volatile for the purposes of simplicity to trick us to begin with?
Kind of, yeah. I mean, you mean this page?
No. You showed what the device manufacturer gave you with the macro. You had the lovely while, like wherever it's
Yeah, I know what you mean. Yeah.
That
Okay.
one, so
Hidden.
read bit, did it have volatile in there?
Yeah, absolutely.
Okay,
Yeah.
yeah.
The manufacturer code is all written in C, and they've got all this. Everything is volatile from the manufacturer. Stuff that doesn't need to be volatile is volatile, and it will. They don't really care. They just kind of blanket. Hey, it works. Don't worry about it. Oh, I've skipped ahead. That was the bit I wasn't supposed to do. Anyway, yeah, at this point I was going to ask for questions, but then, is there any more questions? Because this is kind of weird. I haven't seen a talk like this at CPP London before, so I have no idea whether I'm getting through to anyone or whether this is stuff you care about. So I thought maybe, no, I'm just going to skip ahead. So the next problem that I'm going to talk about is code size. And it's a big complaint for people that write normally in C in embedded and might want to make the transition to C++. They might not want to do it because their code is going to be massively bloated. And the reason for this are the features of C++ that kind of have cost inherent with them, whether you use them or not, which tends to be exceptions, runtime type information and spread stage statics, whatever the hell they are. So we switch them off. When we invoke the compiler, I don't know how well you can read that, but we basically switch these features off, which is fine, right? It's okay. It's okay. It's okay as long as we don't use the standard library. Because the standard library well, there's loads of the standard library that doesn't do things like allocating or have exceptions or whatever, but a lot of it might. And you kind of don't know, and you would probably have to delve into the implementation to find out, because they're completely allowed to. Everyone's allowed to do exceptions and stuff in their code, in their implementations of the standard library. So if you do happen to use the standard library and you do call code that can throw, or does throw, or might throw, then you're UB, you're undefined. That's just kind of how it is. But yes.
Just a quick question. Generally, on a microcontroller, you definitely wouldn't use standard library.
No, maybe not. But maybe you really kind of just want to get something done real quick and maybe stood Q is the answer.
It would even fit in its ROM.
No? You don't think you wouldn't fancy a bit of type traits?
Definitely not.
No? Okay, I love type traits. And I love the standard library. I'll use as much of it as I can that I can kind of reason about that it's not going to do this kind of stuff.
This is like, I apologise I'm saying this now, when
No,
you're
don't.
so many slides beyond where the original one, you had this nice
Yeah.
thing that had about the read-write registers,
Yes.
this
These
one,
ones.
and you had the second and the third, said writing is undefined behaviour, reading is undefined behaviour.
Uh-huh.
So
Well, actually, all of this is undefined behavior because the compiler, the C++ standard has no concept of any of this. This is the C++ compiler, and the standard thinks that this is memory. This is like RAM, but it's not RAM. But it is, but it's not.
So, is it your use of undefined behaviour rather than what you might go and pick up in the standard? It would say this is undefined, this is implementation defined, these kind of things. You're saying the embedded compiler you have that accepts these things, knows how to go and set these addresses and stuff like this. When you use that in combination with the device, if you're looking at the device spec and you're going and doing these things, hey, who knows what's going to happen? Demons are going to fly out your nose because we don't know what's going on.
Yeah, I mean, my folly is for using a high-level language at all to do any of this stuff. I should just be using assembler for everything, right? But I mean, C has the same problem as this because it's really very kind of loosely defined what happens in these scenarios.
I think it was more, I was picking up on the use of undefined behaviour as you might have it in the standard versus your interpretation of auto writing, because I don't know what writing to those volatile addresses would even say in the standard. Maybe that is, or maybe that's implementation defined behaviour, and then you're saying when you're doing that implementation defined behaviour in combination with an embedded device, and you look at the spec of the embedded device, then you're like, oh, who knows what's going to happen.
Right, yeah. So normally, when you're doing something like this is implementation defined behavior. because it's not really undefined behavior. There's like a system in place for doing this kind of, I guess, is it type punning, or it's not quite type punning. It's kind of, you're just reading a memory location, and it should be fine. But the problem comes from this stuff, from the fact that it isn't really memory, and it's going to have these weird behaviors that aren't expected. So that's where the problem is. That's where you go from implementation defined behavior to undefined behavior, like kind of sneakily, because of this. Is that what you're getting at?
Yeah, I am very much getting that, and I just don't know if that is classed as undefined. Like, I don't know.
Yeah, maybe not. I don't know.
My point here was, it's not undefined behavior as you might read in the standard. It's if you do this stuff, which is implementation defined on this little board, and you read the device specs of this board, then who knows what's going to happen? And maybe that is undefined behavior. It was more, you use undefined behavior, and I was like, I don't know if that's the correct. I'm not trying to pick holes, honestly, genuinely.
Yes, it's almost.
Like, I don't know if that's the right. Maybe it is the right term. I just don't know.
Yeah, and maybe not. Maybe it should be like device-defined behavior.
Maybe you have a new term. You're now on your way to success.
Yeah, maybe we need a new term. We probably do for all of this stuff, really. There's another question, I think, just behind you, Tom. Yeah?
Just wanted to, when you had all of these registers, the bits, in these particular cases, wouldn't you use like a volatile struct to kind of and have a bitmap to exactly the registers and whatnot? You know what I mean?
Yeah, I get what you're saying.
Each bit represents something, so instead of trying to kind of imagine what they are in void and kind of as memory addresses, if you can just reinterpret cast into a bitmapped struct, you kind of have access to the named parts of it, and now you're on the way to success instead of trying to guess what you're doing, right?
Sure, yeah, you could do something like a read-only bit, you could just make like a const value, right? And that would kind of make sense. But you're not going to do that necessarily, because you're going to do a project and you're going to have a header that was given to you by the manufacturer, and it's just a C header full of structs that also don't know these things. It doesn't tell you that the bit is read clear 1 or read clear 0 or something, because for them, I guess it's too much work to actually fill that up. And no one's really that interested, because whatever, you're going to do it and it doesn't work, and then you're going to go through your debugger, and then you're going to find the line that breaks, and then you're going to just hack it until it works, right? That's the mentality. I kind of would prefer it if the compiler knew about this stuff, not only so that it could tell me when I've got it wrong, or when I've misinterpreted the documentation perhaps, but perhaps it can tell me, or perhaps it can optimize for some of these things, because maybe if stuff is const only, then it can know that, and generally optimizes quite well for stuff that's constant, right? But maybe I'm barking up a very, very weird tree, and I'm definitely not explaining myself very well.
I think my complaint about what you just said is, though, if you want to go and have it so that the compiler knows what's going on, you've got to have custom builds of the compiler to know exactly, I've seen a write to this particular bit, therefore I can go, it means this, and then you've gone from, I've just made a little device, or I can make my little SDM chip that I can just go and use, and off-the-shelf GCC that targets, I don't know, I'm going to say PowerPC, look out there, showing what I used to do for a job. And yeah, there's a big step there from just being able to run, you've got a really simple ARM chip, and then now we've got to go and have a compiler that knows what all of these addresses are, and you've highlighted the horrible C that gets pushed out by the device manufacturers, and now you want the device manufacturers also to go and have their own builds of GCC and things like that, which, that makes me scared.
Well, yeah, I guess that would be scary. But if it was defined by the standard, then all compilers would know about this stuff. And it might be useful because it's not just microcontrollers that have these features. I mean, it's very obvious for microcontrollers because we tend to program them in bare metal more often than you would ever do for PowerPC or something, right? You would normally run an OS on that stuff. But you get low enough level in that stuff, and this is what it looks like at the very low level of any CPU, any
So
chip.
you're not talking about the particular registers or peripherals, you're just saying for these particular, how many there are on the thing? 8, for these particular 8, you want to have something in the standard that says these are 8 kind of embedded things, this is what their behaviour means, and then somehow, but again,
Maybe.
I don't know how it comes like full circle. Even if you define what these mean in some kind of standard, how when you're then compiling the code that you showed for doing Blinky, how do you as a developer or them as a device manufacturer and then a compiler manufacturer know that that particular bit means this? Because I presume on the SDM mode you're talking about, you get lucky it's got an LED, and maybe in the real one that you put in your really embedded device, there's no LED there, it's somewhere else.
Right, so what you're saying is that it would be a lot of work.
Yeah.
Yes, it would be a lot of work. However, they've kind of already done that work. Like you saw the documentation I showed earlier. That work is done. That is defined. And they even put out like XML stuff where it describes all this stuff. It doesn't, sometimes it goes into this level, it's supposed to go into this level because ARM specify that it should go into this level of detail. But it often doesn't. It just goes into kind of the minimal so you can kind of generate a header. But that is what they do. They generate a header from that documentation. And that's kind of more like what I would expect to do. I might not expect like to change the whole world and have it so that the standard knows about all these kind of things, but maybe to have a concept of memory mapped stuff, memory mapped hardware would be kind of cool, because then I wouldn't have to really be scared about doing this kind of thing. Maybe I shouldn't be scared about doing this kind of thing because it works. I do it all the time. This is what I do for a living. And should we get back to it? I mean, I was nearly finished anyway, to be perfectly honest. And I can't remember what I got to. Yeah, so I was about to get into this kind of thing where I'm going to say that the reason that this is all UB is basically because these concepts aren't known by the standard, or they are kind of known by your compiler, otherwise you probably wouldn't be using it at all. But it's not really very well defined. So my wish list is for currently a few things. One is Herb Sutter's exceptions, because I really like that, and that means I don't have to switch off exceptions anymore, this kind of thing. That would be really, really, really handy. What it basically means is that you would kind of have the option to, rather than throw and like kind of try and catch kind of thing, you would kind of, presumably, you would reply to all your function calls down the stack with your error. Something along those lines. But it's worth looking up because it's very, very clever, and it's Herb. And it would be cool for the standard to know, or have some sort of concept of the memory that isn't actually memory. So in conclusion, using C++ works. It's kind of fine. I should, like you say, I should probably do something about it if it upsets me this much, right? And or maybe just use Rust, which seems to be a popular option at the moment. Anyway, thanks. That's it. That's all I've got. But have we got time for questions? Yeah.
Thank you for your presentation, and sure. I'm really jealous about work so close to metal.
Yeah.
But the question is like high level. You showed horrible manipulations in C++, at least to my taste, they're horrible.
Yes, absolutely
and
horrible.
The question is, would be like, and the amount of effort needed for this, like, is C++ or C a right tool for doing this, and why not other tools? And also, if you could elaborate on Rust, why would Rust be better? But
right.
like Rust aside, like why not some other tools which might fit these abstractions which are essential here and completely missing in C++?
Yeah, I mean, this is basically assembly, right? I mean, the assembler wouldn't be much bigger than this. It would be pretty much the same thing. You just load these numbers in and write them to the memory, and you would be very confident that it's going to work how expected. And you could get all your numbers from a manufacturer's header where they tell you what these addresses are. But I guess most embedded code, like really bare metal, doesn't look like this anyway. I mean, this is what it's doing, but it's all kind of hidden behind lovely like macros and structs, you know?
humanity was doing embedded development for ages, and
Yeah.
why there is no better, like, higher-level language which shows all these abstractions, which would...
Yeah, I guess that's a good question. Maybe there is. I don't know. I never really had the option. I mean, most embedded devs are glued to C, and you can't really argue it out. I went to C++, luckily, because when I joined Roli, there were a lot of people that were very well versed in C++. And they knew their stuff, and it was great to learn from them and see what the kind of tricks that could be used for this stuff. Particularly things like templates, which can allow you to do a lot of very interesting optimizations for this kind of thing. But the real reason why you wouldn't want to write all your embedded code in assembly anymore is because it would take a very, very long time to do that. Especially if you were making something like this, it would be absolutely nuts to do that in assembly because it's a big project. You've got a lot of sensors and you've got a lot of communication routes and things going on all the time. And it would be kind of crazy. Not impossible by any means, and you'd fit it on a much smaller device probably, but I don't know. I guess, I don't know whether I've answered your question very well.
You did, thank you.
Sure.
So we talked a lot about volatile, which is obviously right at the centre of this.
Yeah.
But one thing you didn't mention, I don't know if you've been following the deprecating volatile proposal that's going through at the moment.
Oh yeah, I heard about that the other day. I'm quite intrigued by that. I think probably the embedded use case is the only thing that's it's going to be left in for, right?
Definitely the main driver. I've not been following too close. So some of the initial presentations and I've been very time to follow. Obviously, it's clearly defined in terms of what we're trying to take out of the standard.
Yeah.
But I think in doing so, they're also looking at what we really use it for, what the actual use cases, because there are no ways to do that. So I think being part of that conversation is going to be really valuable. If you've got specific ideas like this, whether you want to sit down and represent it.
Yeah, well, I mean, a lot of what I've kind of touched on with the hardware can kind of change the value from underneath, like while you're trying to read it. It's a little bit like kind of multi-threaded programming, for which you've got still atomic. But as you've seen, we probably shouldn't be using the standard library, so still atomic's kind of out, and probably doesn't quite solve all the problems either. I don't know that they must have thought of something to put in. I mean, there's people like Sada that do this kind of stuff, right? So whatever they remove volatile for, they'll either put something back in space. You know what they're doing? Or you want another question?
I'll answer that, but I just want to say, just to be clear, the title of deprecating volatiles, get clickbait. They're actually talking about completely removing the volatile keyword.
Yes.
Just removing some of the places that applies and hopefully makes sense.
Right, okay.
But still concentrating on what's left.
Yeah, I mean, it'd be cool to actually have a proper definition for volatile, because it seems to be a little bit different depending on the compiler who you ask about that.
So I'm not completely up to date with the removing volatile proposal, but what I remember from reading it is that they proposed a couple of sort of magic functions, that there's going to be something like volatile load and volatile store, that the compiler would know, okay, this might change since the last.
Okay, that'd be nice.
Well, so yeah, don't take that as gospel, that's just like from memory.
Yeah, I only heard about it the other day at the Audio Developer Conference when they were talking about kind of new stuff.
Also, while I have mine, your very last line was use Rust, question mark. I don't know if that was just a flippant throwaway thing, or whether you were vaguely serious. And if it's the latter, what is it that Rust offers that C++ doesn't currently?
Currently,
wouldn't you just have to use unsafe everywhere?
Right. Yeah, I mean, unsafe is basically what you have to do because it's clearly unsafe. So it's not like a very good solution to this stuff, but it could be, right? Because I mean, they change Rust so often that you could just kind of shoehorn in a definition for this kind of stuff if you wanted to. And a lot of people are kind of going in that direction because for C developers, it's a lot easier to sort of imagine going to Rust than C++ because of the misconceptions about how C++ used to be before like C++ level. And, you know, the kind of optimizations that we have now that they didn't have back in the day when they would take their C and compile it in C++ and then it gets massive. It's not like that anymore. You can build the same program in both languages. Yeah, Rust is kind of interesting because they're doing a lot of work for kind of generating this information from the documentation. So they're kind of getting a leg up on just kind of making it very, very easy to program, to get started programming microcontrollers and stuff in Rust. It's incredibly easy to do that, and you kind of don't have to worry about, you don't have to worry about this stuff most of the time anyway, but you really don't have to worry about this stuff, well, unless you're one of the people trying to improve Rust. Does that not answer your question?
I was going to say, in theory, we could generate a nice looking C++ header instead of a C1 with all these macros. In theory, you could generate a nice C++ header instead of all these C1 with all these macros and stuff.
Yeah, and people do that. Yeah, we should encourage that kind of thing. But it's kind of not the norm, unfortunately. This also isn't the norm, but yeah, sorry.
What for Rabbit knows memory writes into functions that's slightly on the rack, and then parentheses loops will be a line inside or something like that. So instead of doing this memory writes directly, instead of making compiler doing it for you, just write it to functions, and then implementation of those functions will do it via inline assembly. So
yeah, that's.
Doesn't affect the place.
I think that's one of Odin Holmes' approaches. He's a much cleverer person than I am doing this kind of stuff, and he's got a fantastic library, or probably several, for doing memory mapped kind of interactions. Some of which can be very cleverly sort of optimized by his system. Unfortunately, it's extremely template heavy, so it's totally verbose to. It's impenetrable for me as a. I mean, I haven't been doing C++ long enough, I guess, to be able to read a lot of the stuff that he's made, but it's extremely clever and powerful. But that's the kind of thing that I think that it does. It would use kind of intrinsics and inline assembler to do these memory operations kind of more safely. Thank you.